So let's now talk about sets, real numbers, and numerical expressions. So we all know what numbers are, and here's some examples. The number 9, the fraction 3/4, the decimal 45 hundredths, and one number that you might not think of very often, pi, which is basically the ratio of the circumference to the diameter in a circle. Pi is not a variable, it's an actual value. It's approximately 3.1416, but it is a non-repeating decimal that goes out to infinity. What do we normally do with these numbers? We usually do some kind of operation on them. We could add the numbers, we could subtract them, we might multiply, and we might divide them, or we may do a combination of this. When we do combine numbers in operations, addition, subtraction, multiplication, division, these make up what we call a numerical expression. So let's look at some examples of numerical expressions. Again, taking numbers and putting operations with them, combining them with operations, results in a numerical expression. So 9 plus 3/4 is a numerical expression. 45 hundredths plus pi, since pi is a number, is also a numerical expression. But in algebra, we're usually looking for some kind of an answer. Since we don't know the answer when we start out the problem, we use some kind of a placeholder for the answer until we are able to find it. We refer to this placeholder in algebra as a variable. So when the variable is used in the operations above, for example, the 9 plus 3/4 above, but now we add a variable to it, we have what's called an algebraic expression. So let's take a look at a couple of algebraic expressions. 6x plus 3, because it has operation addition, it has numbers, and it has a variable. Pi y minus 9, the same thing, except what is the variable in the above expression? Make sure you understand that it's y and not pi, because again, pi is 3.1416. And then finally c divided by d. There are no numbers there, but there are variables there, so we still refer to that as an algebraic expression. One thing about multiplication, you don't actually see a multiplication sign when we're talking about 6x or in 6 times y in this example. We don't write it as 6xy, and hopefully the reason is obvious, because that would be very, very confusing. Rather, we just write 6y, so multiplication is inferred. You may see in physics course, for example, where they actually will use x for times, but we will never ever use x for times in this course. So generalization. If I want to write x times y, what are valid ways to do it in this course? We can say x dot y. We can say x times the parentheses, y close parentheses. We can say parentheses x, close parentheses y. We can say parentheses x, close parentheses, open parentheses, close parentheses, with x's and y's in between them. Or the most common way we will say it is just xy. So they all mean x times y. We will probably use all of them in one case or another. If you remember, division is just the inverse of multiplication. For the division operator, we can write it two ways. We can say x divided by y here, or more generally we will say x over y, as shown here. So let's take a look at page 2 of our text. It starts out by some familiar concepts, for example, addition, 4 plus 6, and then it gives an abstract equivalent, and then finally the English language explanation of the concept. So let's take a look at it. You can see we have operations we're familiar with, addition, subtraction, multiplication, and division. And as you get farther to the right, especially under the algebra column, you see the abstract equivalence of them. We don't have 4 plus 6 anymore. We have x plus y. And then in English, we say the sum of x and y. Likewise, we have that for subtraction, multiplication, and division. Let's now talk about sets. Sets are very, very important in mathematics, and from the definition you could probably see why. A set is a collection of objects. We have to classify them somehow to work with them. So sets are a starting point. And we use braces. You can see the braces here to denote a set. So let's look at some examples of sets. Let E be the set of even numbers between 1 and 11. So E is the set consisting of the numbers 2, 4, 6, 8, and 10. 12 is not in the set because it's not between 1 and 11. And 5 is not in the set because it is not an even number. To demonstrate that sets don't have to contain numbers, let's let W be the set of all cities in Wake County, North Carolina. Then here is a listing of all the cities, at least for now. That can change, obviously. So the purpose of the second example was to show that even though elements of sets are usually numbers, they do not have to be. So let's dig a little bit deeper into sets. First of all, they can have an infinite number of elements. If you look at the set of integers greater than 0, we can write it as I is 1, 2, 3, 4, 5, and we'd have to keep writing forever because the set never stops. So we have a couple of shorthand ways to do it. One is to use the little dots, as shown here. That means keep going using the same pattern. And probably a more mathematical way is I is equal to the set of little I such that, the vertical line means such that, I is greater than 0 and I is an integer. And we describe this as set builder notation. And I already read it to you. A set can be empty, and we call that an empty set or null set. It just means that it has 0 elements in it. And we denote it a couple of different ways, by brackets with nothing in between, or by this indicator, which is like a null sign. For example, if we took all of the cities in Wake County with populations exceeding 1 million, we would have a null set. Because if you take a look at all the cities in the set W in the previous slide, none of them, at least for now, have populations greater than 1 million. So we refer to the objects in the set as elements or members. So the number 2 is an element of the set I above. You can see that it's actually in that set. And we use the notation to say 2 is an element of I. But we already pointed out that some numbers were not in the set I above. For example, -3 is not. So we would write 3 is not an element of I. So it's the element sign here, and if it's not an element, you just strike through it, as you might expect. We also have instances where we have subsets of sets. So let's define that. If we take a set A and we find out that all of its elements are also elements of a set B, then we use the terminology subset. A is said to be a subset of B, and we denote this by A is a subset of B. So just like greater than signs, we always point the opening to the bigger, in this case, set. So A is a subset of B. So our set W that had all the cities in Wake County, and suppose we have a set N, which is the set of all city names in North Carolina, then obviously every city in Wake County is also a city in North Carolina, so W is a subset of N. But for example, Charlotte is a member of the set N, but Charlotte is not a member of the set W. If two sets contain the same elements, they're said to be equal. But this is regardless of order. This may not be intuitive, but really if you look at these two examples of S and T, even though I have the order different in T, I actually have it backwards, the sets still have the same elements, and therefore the sets are equal. We define that to be equal. However, if we get a set that doesn't have the same elements, now U is pretty close to S. S has 2, 4, and 6 in it, U has 2, 4, and 7, but they are not equal sets. Everything has to be equal for them to be equal. They have to contain exactly the same number of elements and exactly the same elements. So let's talk about real numbers, which we'll work with in this class. We actually won't give a precise definition of what a real number is, but let's rely on our experience, common everyday arithmetic, to really help us understand what a real number is. There are different types. There are the integers, and you may have heard them as whole numbers. And these are just basically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on out to infinity, and also 0, minus 1, minus 2, minus 3 down to negative infinity. So if we just go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out to infinity, we have the positive integers, and same with the negative integers. These are the ones that are in the set I of integers that are less than 0. So that's the integers, positive, negative. I don't care whether you call 0 a positive or a negative integer for the purpose of this class. Let's talk a little bit about rational numbers. If we take integers, and we know what integers are, and we put them as fractions, we have rational numbers. So let's take a look at these examples. We have the integer 3 divided by the integer 5. We commonly refer to that as a fraction 3/5, but it was formed by expressing integers as a fraction, numerator and denominator, which we'll talk about a little bit later. Likewise, 2/3 is the same thing. Even 0 divided by 4 is a rational number. I mean, that is 0, but that's okay. Now, we don't want 4 divided by 0 because we're not allowed to have a 0 denominator. That is, for the purpose of this class, undefined when you have a 0 in the denominator. You may not think of 5 as being a rational number because it's not the ratio of two numbers, but really it is, because 5 is 5 divided by 1. You may not think of a decimal as a rational number, but remember, decimals can be referred to as a ratio of something over 10 or over 100 or over 1,000, depending on how far out the decimal goes. And you may also not think of as 5 1/3 as a rational number, but just remember that's the same as expressing 16 divided by 3. So these are all examples of rational numbers. So now that we know something about integers and rational numbers, can we say that integers are rational numbers? Is a set of integers the subset of the set of all rational numbers? And the answer is yes, because if you pick any integer, let's say 7, it's the same as 7 divided by 1. So yes, that's a valid conclusion. What about the conclusion all real numbers can be expressed as rational numbers? And that one is wrong. We don't really prove it in this class, but the number pi is a real number. It's 3.1415965285595 out to infinity, and it's actually been computed to millions of decimal places. But you will never ever be able to express pi as a ratio of two integers. You might think, well, some people say it's 22/7. That's not exact, that's an approximation. So we cannot conclude that all real numbers can be expressed as rational numbers. We can say all rational numbers, the set of rational numbers is a subset of the set of real numbers, but we're not too concerned about that in this course. So I already touched on this in the last slide. Some real numbers just cannot be expressed as a ratio of two integers. I already mentioned pi. Another example is the square root of 2. You just cannot express that. It's 1.414 approximately, but you cannot express that as a fraction. And we call these irrational numbers. You might conclude that there is a hierarchy when you talk about integers, rational numbers, real numbers, irrational numbers. So using our subset definitions that we defined a few pages ago, the set of integers is a subset of the set of rational numbers. Again, that's because 8 is the same as 8 divided by 1. So all integers are definitely rational numbers. The set of real numbers consists of the subsets of rational numbers and irrational numbers. We can't prove that, so we'll have to just accept that in this course. Are there other types of numbers besides real numbers? The answer is yes, but in this class we'll only focus on real numbers, except we will get into complex numbers in one chapter. You may already have a good idea what equality and inequality are, but we have to basically define them in algebra. So we've been talking about numbers. It doesn't matter whether they're integers, rational numbers, irrational, etc. If they are the same, then we say they are equal, and we use the equal sign. For example, 7 equals 7. 5 plus 3 equals 8. It's because we know from everyday arithmetic that adding 3 to 5 produces 8. So we basically have 8 equals 8 in that expression. 3 times 4 is equal to 12 because we know our multiplication tables. And finally, 45 divided by 9 is equal to 5. Now obviously they're not always going to be equal, so we use the inequality sign, and math is pretty consistent that we just take the original sign and strike through it. So 6 does not equal 7, and more importantly, 4 times 5, which equals 20, is not going to equal 21. So we will use this in our algebraic expressions involving variables. We may think we know all about equality, and we probably do, but in mathematics we need to state what we believe is obvious and intuitive, and we may not be able to prove it, so we state it as properties, and we use those properties to develop other areas in algebra. So let's go ahead to the next slide and talk about those properties. So let's begin with the properties. The first one is pretty obvious. A number equals itself. Mathematically stated, the reflexive property says for any real number a equals a. The first two are pretty obvious. 10 equals 10, n equals n. May not be quite as obvious that a plus b equals a plus b, but you still have just numbers on each side. Note that we're not yet stating that a plus b equals b plus a, but we will pretty soon. Next we have the symmetric property. So if A equals B, then we say B equals A. It just means you can turn them around the equality. And that comes in handy because sometimes we are a left to right reading society, and sometimes it'll be more important to flip it around so it makes more intuitive sense to us. So if 12 plus 1 equals 13, then 13 equals 12 plus 1. Likewise, if y plus 2 equals 6, then 6 equals y plus 2. So that's the symmetric property, and again, that's for any real number, a and b. The transitive property gives you some kind of an intermediary. So we have a, b, and c now, and we're told that a equals b and b equals c, so we can conclude that a equals c. So they both a and c are equal to that intermediary b, so they have to be equal. So take a look at a couple of examples. Well, we know 4 plus 6 equals 10, and we know that 10 equals 5 plus 5. So the 4 plus 6 is the a, the 10 is the b, and the c is 5 plus 5. From transitive property we can say 4 plus 6 equals 5 plus 5. More algebraically, if a plus 2 equals b and b equals 5, then a plus 2 equals 5. Again, the intermediary is b, and we can set a, which is a plus 2, equal to c, which is 5. So let's take a look at the substitution property. For any real numbers a and b, where a equals b, a may be replaced by b, or b may be replaced by a, in any statement without changing the meaning of the statement. That means you're keeping the statement as true as it always has been. So here's some examples. If a plus b equals 5 and a equals 2, then 2 plus b equals 5. The statement has not changed. You just gave me a little more information. You started out with something that I can't solve. You gave me a little more information, and instead of a over here, I'm going to put a 2 in for a. Now you gave me something I can solve, but we won't solve it at this point. Next one, if x minus y equals 9, or you could almost say but y equals 4. Why have a y there when you could have a 4 there? Substitution lets you say x minus 4 equals 9. So we made it a little bit simpler by substitution. Last example, if c plus d equals 5, and c is equal to x plus 2, then x plus 2 plus d equals 5. And you'll say, why'd you do that? It looks like you made it more complicated. Well, maybe. It depends on the problem. We'll get into those later. All I'm demonstrating here is the fact that I can validly substitute x plus 2 in for c over here to get x plus 2 plus d equals 5. We have talked about addition, subtraction, multiplication, and division as operations so far in this course. And remember, we had a numerical expression, for example, which consisted of these operations and numbers. So do we just do it from left to right, or how do we proceed with the operation? So let's take an example. We have this numerical expression. I don't even want to read it to you because that may imply that it should be performed from left to right. Is it really 20 plus 60 divided by 10 times 2? Or is it 20 plus 60 divided by 10 times 2? Or is it 20 plus 60 divided by 10 times 2? So I tried to change my vocal inflection to assist in figuring out what order the operation should be performed in? Well, algebra takes away the guesswork from us because we have rules. So we have to have a procedure that everybody agrees upon. I mean, there is no right or wrong here until we come up with a procedure. So before we list these rules, let's talk about these symbols of inclusion. So we have symbols of inclusion being parentheses, brackets, and braces. Here's an example. We have 6 plus 7, and because we have symbol of inclusion, I would read this as 6 plus 7 times the quantity, 3 times the quantity, 4 plus 6. So there's a strong implication, the way I read it, that maybe you're going to add 4 plus 6 first, because they're the innermost, then, which is 10 of course. Then you're going to multiply by 3 to give 30. Only then will you multiply it by 7 to give 210, and then finally you add the 6 to get 216. But could you have said 6 plus 7 is 13 times 30, which gives you something other than 216? So we have to have order. So let's talk about that on the next slide. So here are the rules. When you have symbols of inclusions, the braces, the brackets, the parentheses, you perform the operations inside the symbols of inclusion and above and below each fraction bar. You do that first. If you have more than one inclusion symbol, you start with the most inward one. Then you perform all multiplications and divisions in order in which they appear from left to right. Finally, you perform all additions and subtractions. So this can be very confusing rules. Let's go on and look at some examples and try and simplify it a bit. Okay, here are the examples. We have this numerical expression to simplify. There are no symbols of inclusions and no fraction bars. So we proceed to rule 2, and we do the multiplications and divisions from left to right. So we have 20, it's this 20 right here, because that was an addition. And we do this first. 60 divided by 10 is 6, sorry. 60 divided by 10 is 6, and then times 2. Well, we could have done it all in one step, but now we can do this multiplication, and we end up with 12. Now we can finally add 20 to it. That's still too confusing, I believe. So I would have restated the problem as this. There's no doubt at this point that you still use the rules, but you do the rule 1 now applies, and you do the innermost symbol of inclusion. So 60 divided by 10 is 5. Then you have inside the brackets 5 times 2 is 10, and then you have no more symbols of inclusion, so you just add 20 to it. And it's important to note that this is the way they'll all appear. So do you have to memorize the rules? No. Do you have to understand symbols of inclusions? Yes. So simplify 5 plus 2 times 3 plus 4. Again, you have symbols of inclusion, and you do not have an innermost one. This one is equal, as far as innermost, they're equal. So you do the 5 plus 2 and you have 7, and you have do the 3 plus 4 and you have 7, and you just end up with 7 times 7. Again, the multiplication is implied if you remember back to our earlier discussions. But I put a dot here to show it's 7 times 7. I could have had both 7's in parentheses. So now we go to a division problem. So leave the fraction bar to last, evaluate the numerator. Again, you have symbols of inclusion, so 8 divided by 4 is 2, times 6 is 12, and then you can subtract off the 2 and get 10. And likewise, the denominator would be 20 minus 18, which is 2. So you end up with 10 over 2, which is just 5. So we are finished with section 1.1. Take a look at these problems to make sure you understand that these are not the homework problems.